In this video, we're going to talk about integration by substitution and how it pertains to indefinite integrals. A big focus of this video is anti-differentiation of a composite function. It's like the chain rule, but in reverse. So a lot of it is pattern recognition. So remember, the thing behind an integral is a derivative. And so when we anti-differentiate, or when we integrate, we're looking for the original function, the thing that produced that derivative. So a lot of that is recognizing, all right, what part of this is the chain rule? What part of this resulted from the chain rule? So it's recognizing, okay, what is f of g of x? And there's a lot of different ways to think about this. So one thing is your g of x here, so it's f of g of x, so that's your inside function. F is obviously your outside function, that's what a composite function does. And then remember in the chain rule, right, you take the derivative of the outside part and then multiply by the derivative of the inside part. So we have to recognize what's the outside and what's the inside. And let's dive right into an example. So let's integrate this function. So x squared plus 1 all squared times 2x dx. The first thing I like to do in this situation is try to pick apart what's g, what's f of g, and what's g prime. So I notice that there's this times 2x over here, and I'm like, maybe that's g prime. So it looks like I have a function inside another function here. So x squared plus 1 is my g of x, so that means g prime, right? The derivative of x squared plus 1 is just 2x. That works out. So f of g of x is this bigger function here. So x squared plus 1 all squared. And so now that I have all my players here, I've got all my pieces, so I have little f, little g, so f of g of x times g prime of x. Notice that g prime of x doesn't come into play when we integrate, right? Because when we work backwards from a derivative, we're probably going to have less things in our original function. So I find my lowercase f, my little f, up here, which is the x squared plus 1 all squared, and I take the integral of that. So that means that this thing is raised to a power of 3, and I'm going to put that over 3 plus c. So this is the integral of that. And as always, when you start a new process, you always want to check. So if this is the original function y, I just made that 1/3 in front instead of dividing by 3. Because product rule over quotient rule. And I'm going to take the derivative and simplify it, and it is the actual function I started with up here. So let's try another one and see if we can't recognize the same pattern here, but let's try it with a trig function. So let's integrate 5 cosine of 5x dx. So just like in the last example, I'm going to try to find my g first. So I noticed that usually cosine of x is the standard trig function, but I've got a 5x here. So like what you were thinking for the chain rule, you'd have to do something a little different because it's not just x, it's 5x. So that must be my g, and g prime of x is 5, so that means that this 5 here in front, whether it's in the front or the back, doesn't matter, because multiplication is commutative. So that's my g prime, just 5, and f of g of x, right, where g of x is 5x, f is just cosine of that g function, so that's cosine of 5x. And from here, I recognize that I have that same f, little f and big F situation, and remember g of x doesn't change, so it just stays on the inside. So that 5x doesn't change. We just need to integrate this cosine function, which is our little f, and the integral of cosine is sine, so the integral of this whole thing is just sine 5x plus c. And when I check that, if my original function is sine of 5x plus c, the derivative is cosine of 5x times 5, which is also 5 cos 5x, which is what I started with. And so there's another rule here to consider, which is the idea of multiplying and dividing by a constant, which is essentially the constant multiple rule. So this thing here in beige box, we'll go with beige, this lovely khaki box, we can move that constant k out to the front in front of your integral. So that may come into play with something like this. So I have a multiplication here, and it looks like I have a chain rule as well. So I've got the integral of x times the quantity of x squared plus 1 all squared. So just like the last two examples, I'm going to try to break this apart into g and f. So I realize that g could be this x squared plus 1, and f would be that quantity all squared. So The tricky part here is that I just have one x, and is that g prime? Because if g is x squared plus 1, the derivative of that is 2x. So let me show you how you can work this out. So the only thing keeping this x from just being your g prime is that you have a 2x, but 2x times 1/2 gives me x. So that means that this guy is going to come out here. So that's where this rule comes into play. I'm going to pull out that constant. And now I just need to integrate this little f to make it the big F. So I recognize that the big F has to be the integral of this x squared plus 1 all squared. So the 1/2 drops down in front, as all constant multiples do, and so this increases to a power of 3 over 3, and that just becomes x squared plus 1 all cubed over 6 plus c. Something else that comes into play when you work with integrals using substitution is a change of variables. So if you're working with a lot of like f of g of x and a lot of x's, you can always replace that with f of u and define that g as u, just like we did with the chain rule when we were taking derivatives. And so that little f of u, when you integrate it, becomes big F of u. Fun phrase to say. So let's apply that to a couple of examples. Let's first start with this integral of the square root of 2x minus 1 dx. So I noticed that this is a function within a function, so I can define u as this 2x minus 1. And so I also see that the f function is the square root of u. Something else you can consider here, because you're going to need to work in terms of du, so that dx needs to be replaced with something in terms of u. And the way that you do that is if you take u, which is our 2x minus 1, if you take the derivative of u, you get 2 times the derivative in respect to x, because if we're changing variables, we have to also include the dx in there. So if I isolate dx, right, because that's what I want to substitute for, I can just divide both sides by 2, and dx is equal to du over 2. And what I do with that, in terms of u instead of x, is I can replace this square root of 2x minus 1 with the square root of u, because everything is being replaced with u. And dx, remember, is the same as du over 2. And this is like saying I'm going to multiply by 1/2, so I can pull that on the outside. So I'm left with 1/2 of the integral of the square root of u du. So I just rewrite that as u to the 1/2, and then I'm going to integrate this guy, so that gives me 1/2 brought down, u to the 3/2 over 3/2 plus c, and so these two things end up being 1/3 or divided by 3 of that u value. So all I have to do is plug back in what u is actually equal to, which is 2x minus 1. So I end up with 1/3 quantity 2x minus 1 to the 3/2 plus c. And since that one was so much fun, let's do another one. Let's find the integral of x times the quantity of 2x minus 1 all under the square root of dx. So remember, we're going to be looking for things to define in terms of u. So just like in the last example, I have u, which is underneath the square root, so that's 2x minus 1, and the derivative of u in respect to x is just 2 times dx, and again I can solve dx in terms of du, so that's du over 2, and f of u is the square root of u. Now the tricky part here is that I have this x that I need to substitute in for. I have u values for both of these things. So what I'm going to do is I'm going to take this u here, because it has a u and an x in it, and I'm going to solve for just x. So I would add 1 and divide by 2. So I'm going to replace x with this u plus 1 over 2 value. So when I plug in my value of x, I get u plus 1 over 2, and this all here is f of u, so that's the square root of u, times what dx is equal to, which is du over 2. And so if I just simplify this out, I have 1/2 times 1/2, I can pull out a 1/4, so I'm left with this u plus 1 times u to the 1/2, which I'm going to distribute, and we have that du there at the end because that's important. So let's work this out and substitute back in and see what our integral is. And now when I distribute that u to the 1/2 to u plus 1, I get u to the 3/2 plus u to the 1/2, which I'm just going to use the power rule to integrate. So this is what I get when I integrate. I bring down the 1/4, I get u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus c. I work some basic algebra magic, distribute over fractions, and here's what I have in terms of u. And we always want to substitute back in for x because that's the variable I started with. Got to end with it. So this is my final integral, which is the original equation that produces this as its derivative. And here's another one that requires change of variables, but this time we've got a lot of trig functions here. So I'm going to take the integral of sine squared of 3x times cosine of 3x dx. So the first thing I'm going to do here is rewrite this sine squared in terms of sine of 3x all squared, which helps me recognize that u here, because I have a cosine of 3x, u is probably bigger than just 3x. And I'm going to try it with the sine of 3x. So if I do that and I take the derivative, I would have cosine of 3x times 3 times dx. And I recognize that cosine of 3x times dx is the other part here that I can substitute for. So all I need to do to get this bit by itself is divide by 3. So this quantity is equal to du over 3. And so when I substitute in, I have the integral of u squared times du over 3. That's like multiplying by 1/3, which I can take out front. And I have the integral of u squared times du, which is a heck of a lot simpler than this guy. So let's take it through and see what I get in terms of x. So I bring down the 1/3, I integrate, I get u cubed over 3 plus c. That becomes u cubed over 9 plus c. And I replace my u with my sine of 3x. So I get 1/9 sine of 3x all cubed plus c. Or another way to say it is 1/9 sine cubed right here of 3x plus c. Whatever you prefer. So as always, some guidelines for working through making a change of variables when you do integration by substitution. First of all, choose a substitution for u that equals g of x. Usually it's best to choose the most inner part of a composite function, but we saw that, like in the last example, it was smarter for me to take sine of 3x instead of just 3x, so you have to make that choice. But you can figure that out pretty quickly once you take du. And here's your second step, compute du, is g prime of x. So remember, you rewrite everything in terms of u, and then you integrate in terms of u, you replace u to obtain the integral in terms of x, and you can always check your answer by differentiating. Highly suggest that bit. And one final rule or theorem that I want to throw at you before we end this video, and that is the general power rule for integration. So if you see some function here that you have the integral of some g of x to the power of n times g prime of x, that is going to use the power rule that we've studied earlier in this chapter, right? So it still takes g of x and brings it to n plus 1, all over n plus 1, same power rules before, plus c. And what that looks like in terms of u substitution is we have u to the n, right, which is the same as g of x times du, and that becomes u to the n plus 1 over n plus 1 plus c. And then you would substitute in whatever that u is in terms of x, or whatever your starting variable is. And so here are some worked out examples in terms of u substitution and the general power rule that we just discussed. I'm not going to walk through all of these, but you can definitely pause the video and take a look at these. But for example, it's no different than what we've done in the start of this video. So if you had 3 times this 3x minus 1 to the 4th power, I'm going to define u as 3x minus 1, so that becomes u to the 4th times du, and so that becomes that power rule, right? That u, which is 3x minus 1 to the 5th over 5 plus c. And so it's really important to focus on what your u is, and the rest should fall in place from there. So always check that your du helps you out. All right, that's going to do it for this video. Thanks for watching.